All right, everyone. Hello. This is Women in Theorem Protocol Study Group Week 4. And today we have a special guest, Potuz. Potuz is a core developer at Prism, which is an Ethereum consensus client. Welcome, Potuz. Thank you so much for being here.
Hello. Thank you for inviting.
And before we start, could you please tell us a little bit about your experience with protocol, about your role at Prism?
All right. So my experience in the protocol. I am a mathematician. I just got bored during the pandemic because I couldn't work with my kids in the apartment. And I decided to get into crypto. I think I only bought some Bitcoin at the time, 2020. Then I decided to read a little bit more. I found Ethereum to be fantastic and their change to proof of stake. It was happening right then at that moment. I bought some ETH and I said that I was going to stake it. And the Medallia incident just happened right there. So I said, okay, so all of my money is in danger. And I decided to start working to help the kids that were writing the Prism client at that time. And slowly I got involved with them and now I'm working for them. So that's...
Do you do both research and core development?
Well, I am not really doing any research at the moment, but I do still have my grad students and a bunch of responsibilities in the institute. But most of my time is spent in thinking on the protocol.
Okay, but pandemic changed a lot of lives.
Yes, it did. I had a young kid and a baby at the time, so it was hard to work in anything else.
That's great. All right, we are about to start. Ladies, feel free to raise your hands if you have questions during the talk. And Potuz, the stage is yours.
Thank you. All right, so let's get to that. What I want to talk today is actually something that is causing that I'm shocked to see a lot of misconception. Certainly the community gets this wrong, but even among core devs, there's not a clear agreement on this kind of questions. What are the essential properties that blockchain has or that blockchain wants to have? So I wrote 5 properties that a blockchain might have. It could be decentralized, censor resistant, live, fast, cheap, safe, and verifiable. We're going to actually define some of these properties later on. But I wonder, does anyone here feel that one of these properties is not essential? Can anyone actually unmute and tell me one in this list is actually not essential? And I will want someone to give me a guess.
So I find the word cheap can be in multiple terms, it can be understood. So if you would like to explain, what do we mean here?
Perfect. So being cheap, if we actually manage to define it, is going to be a 1.5. It's probably not really essential, but I'm looking for another one.
I think live.
Live.
Because recently I was introduced to a project that used Def to do Ethereum transactions on feature phones. So it was recording the transactions kind of at a later stage, so recording them off chain and then using Def to record them later. So I don't think.
Oh, but by live, okay, so probably it's a good spot to move forward then. Live here means that the chain will eventually be able to continue producing blocks. So that liveness is definitely one of the essential properties that the chain wants. So live here means that no matter what happens, we're not going to be in a deadlocked scenario. And I'm going to have a quote to a paper by Vitalik where he gives a loose definition of this, but it really means this: there's no deadlock, and some block producer or some miner or whatever is going to be able to produce a block that advances the chain. Liveness is something that we really want to be essentially there. So anyone wants to shoot another one?
Maybe fast.
Fast. Well, fast is another one to have. The one that I'm looking actually is decentralized. Decentralized is the only one that is definitely not essential. If we could get, and I've left here in black, the 3 essential properties that blockchain wants to have, which are being censor resistant, being live, I just described what live was, being safe, that I will describe in the next slide what it is, but the red ones, fast and cheap, are properties that we want, they're nice to have, but decentralized is not even essential at all. If we could get censor resistance, liveness, and safety in a centralized manner, we would, because being centralized is always faster, it's always cheaper, it's always better than being decentralized for these kind of things. However, we do not know how to get the essential properties that we want, which is being live, being censor resistant, and being safe without decentralization. So decentralization is just the means to getting the essential properties of the chain. Verifiability, well, before that, safety actually here is two different properties. Correctness, that means, well, I'll define correctness in the next slide, but essentially it just means that this chain cannot have a statement being true and false at the same time. And being Byzantine tolerant, meaning that the chain actually can support either attacks or some nodes that are falling offline or some lack of messages in the chain. These are the three main properties. Safety, that here means two different things, correctness and Byzantine tolerant. Being censor resistant, which means a user can send a transaction and it will eventually appear in the blockchain. And being live, meaning the chain will eventually continue forward. Being verifiable is something that I do not want to emit opinion. People, even core devs, have different notions of what or how essential verifiability is. Should it be verifiable in a watch? Should anyone be able to verify the chain? Should it be verifiable in your home computer? Do you need a big computer? Do you need a small computer? Do you need a huge bandwidth to be able to verify it? Could any person in the world verify it or not? So these are questions that have honestly different solutions, different answers. But the main three are the ones here in black, and we're going to talk about these properties in the next few slides. All right, so I'm going to start from something very, very high level, and I hope that it was shocking to some here that decentralization is definitely not essential, but I would want to get to decentralization and how we deal with it. So a blockchain is, well, it's just a collection of blocks. It's built out of blocks that carry information, that is useful information for the users. This information could be anything. So in Bitcoin's blockchain, the information that a block has is just a transfer from a token to another one. In Ethereum, it's an arbitrary execution of and a change of the status of the world computer. In other networks, there's other things that you can do with those blocks. But the thing is that we need to nodes achieve consensus in two different things. And these two different things are overloaded words for consensus. So we need to achieve consensus on the validity of the blocks, the validity of that information, and we need to achieve consensus on which of the blocks is the current. That is, if there are two blocks that are valid and both of them are not compatible, which one is the one that we should consider for being part of the chain? So these two things are different areas of consensus. And what changed dramatically in the last couple of years on the Ethereum network is the second type of consensus. And this is the type of consensus that I work on. But first, let's go to the first type of consensus, which has to do with this notion of being the chain being verifiable or safety for the chain. So the blockchain for a Bitcoin, for example, the UTXO model, it's not really stateful. It doesn't really have a global state. Nodes keep just the unspent tokens that users had, and that's all you need to validate a full block. Ethereum, on the other hand, has a full state of a computer in what we call the execution state, and users with their transactions can actually modify that state. And what a node does when he has this state with the status of the computer today, or if you're a Bitcoin node, you have the state with the list of unspent tokens or unspent coins and who are the owners of these coins. And when you receive a block with a bunch of transactions, transfers, or arbitrary execution in Ethereum, you make a series of validations, some that ascertain for the block. So for example, the block, regardless of whatever transactions are within the block commits to the previous history of the blockchain. So if you agree that a block is valid, you're also agreeing on the status of the blockchain up to particularly that point. So that's the big thing with the block, is that when you say this block is part of the blockchain, you're already asserting on the whole history since Genesis all the way up to that block. But to verify a particular block, you may not need all of the history of the chain. You need the current state, the incoming block, and you compute the state transition and you get the output state, either the output state on Bitcoin, whomever owns which coins, or in Ethereum, what is the total at the output state of the computer after importing the block. Now, verifiability for Ethereum at this moment, it means that you can, in your own computer, have the state, you get a block, and you can validate that the block it's correct or not, it's the valid block or not. You can compute yourself the status of the state machine without the aid of anyone. So there's zero trust assumption whenever you receive a block on the status being correct after it. And actually, to run a Bitcoin node, I stopped running a Bitcoin node a couple of years ago, but up to not long ago, you really needed, you didn't need much disk, you didn't need much bandwidth nor anything. You could just prune everything. You don't need anything of the history. And the full state wasn't, the full UTXO state wasn't that much. Ethereum today also doesn't require that much. If I remember correctly, the current state, the full state of the machine is about 250 gigabytes. So for current computers, that's not so much. The biggest bottleneck today to validate the chain is bandwidth. You need to have a decent internet connection to be able to follow the chain and get the blocks on time. But that's what we mean by verifiability. How about safety? So safety refers to the fact that you cannot have two contending information. So if you ask a node, who is the owner of this token? Any node that has just synced this block and has the state will reply in the same way. The owner of this token is this account. And it cannot happen that one node will have one owner and another node will have a different owner for the same, after syncing the same block. I'll modify this later when we talk about forkchoice. But the idea is that you cannot have a status in which one person has spent some token in one status and hasn't spent it in a different status, and both of them being part of the blockchain. All right. So that's about what about the validation, and most of it happens on the execution layer. So now I'm going to move to the kind of things that I work on, which I have them dear to my heart, which is how do we decide which block is good? If you receive two different contending blocks that are both of them valid, which one is the true one that corresponds to the chain and which one is not? So here there are two questions. First of all, who can produce these blocks? And second, if you get two blocks produced by players that your system allows, which one is the right one? So these two questions are separate and they require different answers. Principle, you could, as I said already, decentralization wasn't really essential. You could have a single entity that produces all blocks. And now we're going to get to liveness. Definitely, if we do this on Ethereum, we allow only a single person to produce blocks. We cannot guarantee liveness because if that entity disappears or goes offline, then the chain cannot advance by definition. So therefore, we see that some sort of decentralization is needed if we want to have liveness. Sensor resistance, the same. If only one entity is allowed to produce blocks, then that entity can decide never to include your transaction. So a single entity sequencing blocks is not a good status for a blockchain that wants to be live and sensor resistant. But how about a rotating set of only one entity at a time? So if the entity just falls down, then that second entity turns on and starts producing blocks. This will guarantee liveness. I mean, if the list of whitelisted entities is large enough, you will be alive. You can actually guarantee liveness. And this is the approach, for example, that rollups have. Rollups with a centralized sequencer do have this, and they can guarantee liveness, even though there's only a single entity that is actually producing these blocks or sequencing transactions. Sensor resistance is a different story. Even if you have a rotated system of one entity, then that entity that is active at the time can still censor your transactions. And this is the biggest problem that rollups have today. It's very hard for rollups to keep the throughput and the speed and the cheapness of their network, guaranteeing sensor resistance. That's the biggest problem that they have today. Another way of deciding which one is the next block producer is to solve a hard puzzle. This is what Bitcoin did, and this is what Ethereum did before the merge. This is proof of work, and this was the big realization of the Bitcoin network. And this is a very beautiful and simple form of consensus. If you receive two blocks, these blocks will come with a proof that they have solved a hard puzzle, and there couldn't be a tie. You would see which puzzle was harder to solve, and that's the true block. And that's it. Everyone would agree on which of the two blocks is the right one by just looking at the proof of the hardness of the puzzle that they solved. So why would we move away from such a very beautiful and simple system? So the system we move to is much more complicated. It requires people holding a token. In this case, it's proof of stake. Validators in Ethereum, they need to hold at least 32 ETH to validate. And they are assigned at random, weighted by how much they're holding, to produce a block every now and then. So, and this requires a lot of mechanism to actually work. I'll describe this mechanism later on, but why did we move to such a system? I'll leave the question and I'll try to attack it later. But coming back to our set of essential properties of blockchain, here's a theorem. This theorem actually is a theorem of database, but the same theorem applies to blockchain and it applies in many different contexts. So for databases, you have three properties that you would desire to have. You would want the database to be consistent. If you ask the database to read a value, then that database should give you the last written value, or it should error out. It should be available. If you ask the database, give me some value, then the database should return, either even with an error, but it should return. It should tell you, yes, I don't have this value, or this is the last written value. You would also want it to be tolerant in the sense that if you have a bunch of disks and some of them fail, then you would still want to be able to recover the data. So those are statuses that you would want on your database. And in the case where your database is actually distributed, then this partition tolerance refers to you have some messages being around, so you're asking for data, and then this doesn't have it, it requests it from somewhere else. And even if some messages are failing to get to their destination, you still want to be able to recover the data that you're trying to read. And there's a theorem. It's not that new, actually. It's not that old, actually. I think this was proven as a theorem by 2012, that these three things cannot happen at the same time. It's just impossible to have these three properties at the same time. And for blockchain, the same happens. If you want to be consistent, you definitely want to be consistent. You don't want to have this user having spent Bitcoin in the chain and not spend it somewhere else, because you will have this double spending problem. And you want to be partition tolerant. That means that if the chain doesn't send messages from one side to the other one, then you will not be available, which is liveness. Then you might be deadlocked in a situation where no one can produce a block and the chain will stop. Ethereum actually went the other way around. Ethereum set up in a way in which we are giving up on partition tolerance under some conditions to get consistency and availability. So in Ethereum, you will never finalize two unless a third of the network is slashed. You will never finalize two contending branches. And you also are always able to produce blocks. But if there is such a partition in which some part of the chain believes this is valid, and some other part of the chain believes some other block is valid, then what will happen is that those two partitions are going to continue on their own chain, and we will have a breakup in Ethereum, in two different Ethereums. So we gave up that partition tolerance to keep the other two. All right, let's go back to that question. Why the move from proof of work to proof of stake? And it's because we do not know how to get one of the essential properties, which is sensor resistant, without decentralization. We need decentralization to guarantee both sensor resistance and liveness. But sensor resistance is the most important one, and we just do not know how to deal with sensor resistance without decentralization. Before proof of stake, there were only a few miners, and those miners could be bribed to not include your transaction. Imagine if we could have easily had a rollup-centric model for scaling of Ethereum under proof of work. But imagine an optimistic rollup. The node operator removes all of the money out of the bridge, and they can. Someone needs to be validating that rollup, and someone needs to produce a challenge to that optimistic rollup. Or if you're a ZK rollup, someone needs to produce a proof that for the money of that, for that rollup to be continue alive. So in this situation, if you're trying to challenge a rollup because they're trying to steal all of your money, you need to send a transaction for the challenge protocol of that rollup. And if the node operator for the rollup just decided to bribe all miners, then that transaction will never get in, and they will just steal all of your money. So decentralization is the only way of guaranteeing that eventually you will be able to include your transaction. I mean, in the extreme case, if you want to have your transaction in, you can just spin up a node, a validator with 32 ETH, and eventually you will produce a block. Unfortunately, that could take over a year now. But even in the current status of Ethereum, in which there are much less miners than they used to be, because today, most of the blocks in Ethereum are constructed by only two entities, two builders. However, we have mechanisms now to allow the decentralized set of proposers to force transactions to be included. This is an EIP that is proposed, and most probably is going to be in the next fork or the next one or the next one. But in less than a year's time, we hope to have Fossil, which is a mechanism to force transactions in the next block, even if we were not building them. All right, so let's move on to this topic, which is given two blocks, how do we decide which one is the right one? So forkchoice is just literally this. We see two different blocks that extend the blockchain. There's this red one here that is trying to reorg the last black box. Which one is the one that is the right one? And it's important to be able to decide this because these things happen. So our chain actually looks like this. We sent a transaction, which is that red one there. At that block, we send the transaction. If the chain is that in red, then the transaction was in. I need to make sure that my transaction was in. And I can only know that my transaction was in by knowing what the head of the chain is. Because the head of the chain determines the entire history of the chain. And therefore, I can see if my transaction got in the block that is included in the chain or not. So Ethereum moved into a system, the Ethereum consensus to choose what is the right head is a mixture of two separate things that are in contention, actually. And they were the source of many headaches for core devs. One is a finality gadget that allows to say some blocks are not going to ever be reorged. So if a node sees a block and calls it final, it will never, ever move to another block on a different chain and call it final. So an honest node will never, even if 1/3% or 100% of the validators are being slashed, a node will never unfollow a finalized block. So even if 100% of the validators are malicious, a node will never unfollow a finalized block. And then there's another one, which is called the LMD Ghost, which is used to discern between two different blocks that are not yet finalized, but both of them are viable to become canonical. So here, these black boxes are called finalized blocks. So when we are at this stage and we finalize this block already asserts to all of this chain. So whenever we have finalized this block here, this one is final, this one is final, this one is final, this one is final. All of these are final. And moreover, all of these blocks here are no longer viable. A node that sees this block as final can discard all of these blocks because they will never be part of the chain. It doesn't matter if 100% of the validators are malicious and they slash themselves to switch to this branch. And there's some other nodes that are called justified. If you notice, these nodes are just right after the finalized ones. So this node here, justified, and this one was finalized in the previous slide. This one was final, and this is now justified. But among the ones that are not viable, there can be some nodes that are justified. And if you are following what the tragedy that just happened in Holesky, it did happen that Holesky justified an invalid block. So this is the situation that could happen in Holesky when we recover it, that we justified an invalid block, and then the chain switched to another chain and eventually finalizes a valid one. So that's what we're hoping will happen by the end of the month in Holesky. Nodes typically attest, so validators attest to what their head of the chain is. And an attestation sense, so that's what the consensus layer clients do. They just count attestations and then decide which one is the head of the chain. So validators, whenever they see a block and it's their turn to attest, they send an attestation saying, this is my head of the chain today. So a validator that is following this chain will attest during this block saying, this is my head, this is my last justified checkpoint, and here's an arrow, which is an attestation. A node that is following this chain during the same block, the same slot, can see this block, and he will say, well, this is my head, and this is my last justified checkpoint, and here's my attestation. If we could count all of the validators at every slot, that would be all that we need. And this is what we would call single slot finality. That is, validators immediately, when they see a block, all of them would just validate, they would just attest. We will count all of the attestations and decide whether or not that block there was already final or justified or not. So to justify the node, we need 2/3 of the validators attesting for it. If 2/3 of the validators attest for a block, that block is called justified. And if 2/3 attest for a child of a justified block, that block becomes final. So that's the big hope, that we can move to such a system that is pure. But unfortunately, that's very, very hard with a million validators out there. We don't have the machinery to actually count 1 million attestations every 12 seconds. So what we do is we split the blocks, and instead of only being one block, we split them in groups of 32. These are the epochs, and each epoch has 32 slots where validators attest. And then what we actually justify and finalize are the epochs, the groups of 32 blocks. But within each epoch, we actually can reorg and can move and can have very, very much forked situations. So typically what you would see is just a long chain. All of it is finalized, but then the latest one is forked, where there are some reorgs. That's where LMD Ghost plays a role. Whenever there's a block that achieves 66% within the epoch, there might be a block, typically happens on a well-working network by slot 22 of the epoch, which is about 2/3 of 32. By slot 22, we already have enough votes for the beginning of that epoch to be justified. And that's when the chain works fine. All right, so here's a theorem of Vitalik that says that unless 1/3 of more validators are slashed, the blockchain can never finalize 2 contending blocks. So that goes for safety of the chain. And this is a theorem. With our current system, you cannot never have 2 blocks that are contending that are final unless 1/3 of the validators lost all of their capital. So what is slashings? Well, if you're a proposer and it's your time to propose a block, you're chosen in this slot to propose a block. If you propose 2 different blocks, you're slashed. It doesn't matter if it follows from the same chain, or here, for example, you're proposing a block based on B, or here a block based on C. These are 2 different blocks that are contending, and for the same slot, you will be slashed. But the most common type of slashing is attester slashings. And this happens if you need to attest in this slot and you attest 2 different blocks that are contending, you are slashed. This is the most common occurrence. A validator spins up 2 different clients at the same time, and the 2 clients have a different view of the chain, and they vote for different blocks at that particular time, and they are slashed. But there's other kinds of slashing that is slightly harder to understand, which is called the surround slashing. When you attest, remember I told you, you said which one is your head and which one is your source, the last justified checkpoint. It may happen that you have an attestation like this from a later justified checkpoint. Suppose that magically this node attested like this, and then suddenly this block is no longer justified by that chain. This cannot really happen on a well-functioning chain. But that validator, if it did happen to that because of a bug in the software, that it no longer sees this block as justified, it will use this block as justified and then attest in this slot to this head. This is called a surround vote, where the source of the next attestation is before the source of the other one, and the target is after the target of the other one. The same here. This attestation here surrounds this attestation. And this is what is happening today in Cholesky. In Cholesky, we justified an invalid block, restarted the validators, declared this branch as invalid, and now these nodes are attesting with an older justified checkpoint. So this is exactly the situation that happens in Cholesky today. And that's why validators in Cholesky can all be slashed. All right, this is the anatomy of an attestation. An attestation, just to give some technical detail as to how attestations work, an attestation has the slot at which you are supposed to attest, an index which is which of the validators, you are the validator that is expected to attest in this slot, the beacon block root of the block that you're attesting to, the source, which is your latest justified checkpoint, and the target, which is the first block of your current epoch. All right. And this is a theorem from Vitalik where, if regardless of any previous events, like attacks, latency, or whatever, it is always possible for new blocks to be finalized. That is, it's always possible for validators to propose new blocks. However, notice that contrast this with the situation in Cholesky. This is true. In Cholesky, if we didn't, the validators that were running the minority nodes, these were validators that were running with Breath or with Aragon in Cholesky, they could always continue proposing blocks and attesting to them. But the validators that were on the invalid branch, they couldn't. The only way for them to follow the new chain was to restart and actually remove the slashing protection. These validators will never attest for the chain because they would be slashed otherwise, and they don't want to be slashed. So those validators are kind of deadlocked. And it's true that liveness continues, so we would have like many less blocks because most validators will not continue producing blocks on the minority chain. But the point of liveness is that the minority chain eventually sees the other chain as invalid and it forks off. And now you are in a situation where you have two different Ethereums. If we wouldn't have patched the validators in Cholesky, we would have effectively two different Ethereums running in the Cholesky network. That's how is that we accepted that we are not tolerant to partitions. We accept that we might fork eventually, but at the cost of, but in exchange, we get liveness. I'm gonna tell you now a little bit about how clients works. Yeah, so this is the attack. And this is how we count attestations. So on the CL network, so an Ethereum client consists of two different pieces of software, a consensus client and an execution client. And all of the block that contains the transactions, the attestations, and everything comes in the consensus layer P2P network. There are parts of the block that are actually not broadcast with the block. These are the blobs that rollups use. And validators make some very fast verification. They don't check anything about transactions. They only check like things that are kind of be checked immediately. The most costly check is the signature of the proposer that you need to check. So that's the costliest possible check on the block. And you make this fast verification and then you forward the block to your next peer. The execution, on the other hand, the P2P layer of the execution is rarely used on when you're already following the tip. The execution layer relies on the consensus client to tell it what's the current head and what's the latest block that has come. But when you first start your execution client, it needs to sync the entire state, the currently 250 gigabytes. And to do so, they do this completely independent of the consensus client. The consensus client tells it, this is my current head synced on your means to this head. And that takes a few hours typically, where the execution layer on their P2P network, they exchange the full state. Once the execution layer has caught up to the current full state, then the consensus layer would continue feeding it block by block every 12 seconds, the blocks. But transactions are that users send. So the users never interact directly with validators. The users of the chain, they interact with the execution layer. They send transactions through the execution layer. The consensus client gets the block, and it needs to validate both things, that the consensus part is valid, that the proposer was the right one, that the signature was correct, that it was his turn, and a bunch of other things, and the execution in parallel. So the execution was what we said about safety, that the user had enough money to actually pay for the transaction, for example. So the execution consensus client communicates with the execution client via an API, which is the engine API. And it notifies the execution of the new payload that just arrived. If in addition, the new payload that just arrived happens to be valid and it continues the chain, then the consensus layer would tell the execution layer, this is the new head of the chain. Most of the complication of writing a client is in caching the information that you need to validate a block. You need to have a lot of information already in memory to even make sure that the block is valid. You need to know which validator at that time was supposed to be attesting. You need to know exactly the state of the block, what is exactly with the state before starting to process in the block, and everything needs to be already in place in memory. This is for the consensus client. The execution client, since the state is so large, they cannot keep it in memory. So they need to be very fast at caching the right parts of the state that are more often being accessed. They don't need to bring it up from the disk. So you perform the state transition. The block is saved to a database on disk. And before you do anything, you need to save the block on disk, because if you are inconsistent on disk and memory, then you might get slashed your validator. So before you even check which one is the head of your chain, you saved everything to disk, and then you compute on forkchoice what is the new head of the chain. Once you know the new head of the chain, you send an event to every consumer, in this case, our validator clients or signers, that you have a new head. And then you start computing. So this typically happens at the beginning of the slot between second 2 and second 4. And then you have the next 8 seconds to compute all of these things that you need to cache for the next block to be able to process it very fast. So this is the literal last slide, performing duties. A validator client is typically a separate program, or actually 2 different programs, or it might be 3 different programs if you use Vouch. But a validator client is the one that actually performs the duty. So if you are a full node, you need a beacon node, you need a consensus client, but you do not need a validator client. But if you're a staker, you do need a validator client. And the validator client, what typically look, it's following this feed that says, I got a new head, I got a new block, or every 12 seconds, it checks whether or not it's turn to produce a new block or to attest to a new block. And when it is the time to produce a new block or to attest to a new block, it requests through another API, it communicates with the beacon node, and it requests, give me the block or give me the attestation, and I'll sign it. So it signs it with the key. If you're very sophisticated, you will send the message to another computer where the keys are stored, and that computer is safer, and that computer would sign it there, send it back to you, and you will send it back to the beacon via the beacon API to publish to everyone else. So that's how we perform duties. And that's it. So this is more than my allotted time and what I had to talk about in consensus.
Thank you for this. Thank you so much. Yeah, the protocol itself is quite complicated. So just ladies, don't be afraid of it. We should just eat it piece by piece. If you have any questions, please raise your hands or put your questions into the chat. Anything you would like to know about the protocol? What is attestation? Who is validator, etc., etc. For example, Potuz, if I have a node running on my computer, so once a year, I will be a validator, right? I will produce the block. And for...
Yes, you have one validator on your computer. Yes, it's about like once a year that you will be assigned to produce a block, probably twice, but you're expected to produce a block about once a year.
Yeah, and the other time I'm just a tester, right? I attest this block.
Yes, there's a bunch of duties that you need to do. So you are every epoch, so every 32 slots, you're attesting once. So every 32 slots, you will be assigned to one slot to attest. Once in about 3 or 4 years, you will be assigned to give sync committees. So these are messages that are good for light clients. And you will do this for over 27 hours, like every single block for over 27 hours. You also have some duties to serving data to other validators. So you will be requested from other validators that are trying to sync to the chain to get them like a range of blocks from the last, I don't know, how many epochs and so forth. There's a bunch of duties that you need to have, even if you're not even validating.
Got it. Thank you. Vikesh, your question, please.
So you mentioned Holiski. You were explaining that something happened to Holiski. Like I didn't get that. Like what happened? Because you're making reference to it.
So Ethereum goes through upgrades. And even if we didn't go through upgrades, we need to test our software. And it's very hard to test our software in, say, an environment with only like 1 or 2 computers running a virtual network, because we actually need live information as close as possible as mainnet so that we can solve bugs before they happen on mainnet. So for this, Ethereum spins networks that are as close as mainnet as possible, as close as Ethereum as possible. And Holiski is one of those networks that is specifically designed to have a large validator set so that we can test consensus clients. Execution clients don't need that much testing in that sort of environment. But consensus clients is critical for consensus clients to test in that sort of network. So now what happened is that we deployed the next upgrade for Ethereum, the Pectra upgrade in Cholesky a couple of weeks ago. It did happen that the three major execution clients had the same bug. And then it turned out that a block that was invalid was attested by every validator running those majority clients. Since there were more than 2/3, that bad block was justified. And once nodes have justified a bad block, they start attesting using that bad block as their source of the attestation. If you remember, an attestation was an arrow with a source and a target. And they used this bad block as the source of the attestation. So once we fixed the clients, and if we ever want to recover the chain, we fixed the clients. These clients no longer have this bad block in their database. It was pruned. Now they consider it invalid. But now they can no longer attest because their last justified block for them is the last justified block before the bad block. And one of the rules for slashing is that you cannot attest in these conditions. So Cholesky is in a situation where liveness is even threatened.
So you mentioned slashing, right? So please, can you go back to the slide for slashing?
So in proof of work, you weren't assigned to propose a block. In proof of work, let's suppose that the chain was like this. It had 3 blocks, A, B, and C. This is the status of the chain now. And now you're a miner. So miners on proof of work would constantly be trying to solve a hard puzzle. That's what Bitcoin does now. And when they actually do solve a large puzzle, they pack all the attestations that they can and they send a block. But in principle, they could try to send 2 different blocks. But that's impossible in proof of work. So if you send 2 different blocks, they will have 2 different proofs of their puzzles. And there cannot be ties in that consensus. So their 2 blocks would be fine. Both of them would be valid if they're different. But one of them would have solved a harder puzzle. So one of them only would win. So in proof of work, if something like this happens, that you're a miner, you solve 2 different puzzles and you propose 2 different blocks as candidates for D, the chain would just choose one and that's it and continue moving on. In proof of stake, the mechanism is different. In proof of stake, you are a proposer. I'm going to call it miner too, but it doesn't matter. And you are assigned during this slot, during the slot for D, you are assigned to produce a block. And there's no proof that there's no inbuilt mechanism to decide for the best block that you produce. So instead, you could, in principle, produce 2 different blocks and confuse the network. By producing 2 different blocks, you would cause a split, because if you send one block to one attester and the other block to another validator, both of these validators would have seen different blocks and they would think that the status of the chain is different. And that would cause a network split. This is a malicious behavior on a validator. How do we prevent it? Well, we prevent it by, if anyone sees 2 blocks by the same proposer at the same time, and these 2 blocks are different, then that proposer is punished. So this mechanism is the same. So in this situation here, what happened is the proposer produced 2 different blocks. In one of them is building on top of C, and in the other one, he's pretending that this block C never existed and building on top of B. So both of these situations are situations in which a proposer is producing 2 alternative ways of the chain, and this is malicious behavior that we punish.
Wow. Thank you so much. Thank you.
Thank you, Vikesh. Naomi, your question?
Okay, hi everyone. So my question is sort of like what Vikesh also raised. You mentioned that, because I'm looking at the Holisky Beacon chain right now, and I see a lot of empty blocks that have not been validated because of the Pectra upgrade. So I guess my first question would be, what exactly is the Pectra upgrade? Then the second one would be, so now that there are sort of like bugs with the Holisky network, are the validators going to be slashed? Would it work the same way? Because like I see like a lot of like scheduled blocks. I see, yeah, basically like a lot of scheduled blocks. So, and then like it's not justifying, like I see justifying like 22.04%. So yeah, in this case, would the validators be slashed since like is sort of like caused by a bug? Like how does that work?
Okay, so let's deal with the situation in Holesky in a tiered manner, because developers doing something that would not happen in mainnet to try to recover faster Holesky. But let's forget about trying to recover it faster. How does the protocol work in this situation? The situation is that so I'm going to go to something like here. If you look at this slide is like this. So Holesky was working perfectly, had a finalized block, then a justified block, and then suddenly some blocks appeared. This where some validators considered this block valid and some validators did not. So this block appeared here and a validator said this block is valid because it had a bug. The block is actually invalid, but a bunch of validators that saw this block here where I have my cursor now, a bunch of validators saw this block and said this is a valid block. And some validators did not that see this block, they say this is an invalid block. Those validators will not produce, when they produce a new block, they will produce a different block. They cannot produce a child of this block because this one is invalid, so they produce a child of this last justified one. And now validators that see this chain as valid will continue on this chain, and validators that see this chain as invalid will continue on this chain. Now what happened in Holesky in particular is that the majority of the validators were on the invalid chain, which is this one on top. That means that a bunch of them, 66% of the network actually, attested for this block, and they managed to justify it. So this is what happened in Holesky. Now, if we don't do absolutely anything, how does the chain progress? Okay, if we don't do anything, we don't fix clients nor anything. So every validator on this chain will continue on this chain. They will see about 66% or more of the blocks in this chain, except when the validators that are from this chain are scheduled to produce a block. Because when the validators from this chain are scheduled to produce a block, they will produce a block on this chain. And they will ignore it because that chain is, for them, has very little weight. So validators in the invalid chain will ignore this chain, and validators from the valid chain will ignore the invalid ones because they are just invalid. So now over time, on this chain, from the point of view of the validators on this chain, all of these validators here are not doing anything. They're not doing their work. They're supposed to produce blocks, and they aren't. They are producing these useless blocks that are on this other chain. And from the point of view of the validators on this chain, the validators on this other chain are also producing invalid blocks, which is even worse. So the validators on this chain would actually kick them out when they are connecting. So the validators on this chain will not even connect to the validators of this other chain because they consider them malicious, building on top of invalid blocks. Over time, these two forks, the validators in this chain, the state of the computer network in this chain is different than the state of the computer network in this chain. In this chain here, all of the validators on this chain are losing money. They're being punished for not doing their work. And in this chain, the same thing for the validators on this one. So in each one of these chains, these validators have different statuses, different realities. And as the chain progresses, these validators here will kick them out, kick all of the other ones out. So from each one of these chains, all of the validators on the other chain will be completely kicked out and their ETH will disappear. That's the punishment on that chain. And at that point, Ethereum just continues working fine. Both chains will finalize. Both chains will have their validators set voting correctly, and all of the blocks will be proposed, because when this chain already expelled all of the validators from this other chain, none of those validators is going to be scheduled on this chain to propose a block. And every block here will come from validators in this chain, and the same for the other one. But then you will have two different chains that continue forever. So this is one of the trade-offs that Ethereum has taken. We allow this kind of situation so that we are able to continue forever.
Vikish, you want to follow up, right?
Yeah, I just wanted to ask, do we know why this happened?
Yes. What happened is a silly configuration problem and it could only have happened in Holesky. What happened is, for the first time, and you had a question as well, which is, what is the Pectra upgrade? Ethereum upgrades in the sense that the condition for a block to be valid is not the same over time. We add new features, and when we add new features, we necessarily need to change the condition for a block to be valid, because now we support, for example, new kinds of transactions. So we allow users to send transactions that today they will be nonsense, but tomorrow they will give the chain a new utility. So when we do these kind of things, the nodes need to change the algorithm by which they declare the block to be valid or not. So they changed what we call the state transition function. When this happens, we need to do this at a prescribed time and in an organized manner, because every single node needs to agree that starting from now, we support this new feature. And starting from now, we are going to continue the chain with these new validity conditions. Anyone that is running the old software will consider the blocks invalid. So this is what we call a hard fork. When we do this, the chain is set to go on a hard fork. And this is, Pectra is just the name for the upgrade that we decided to test in this chain 2 weeks ago. Now, what exactly happened is that, well, there is a contract. There is one address on the computer that keeps the balances of the validators, keeps how much ETH each validator has deposited, which the execution layer never needed to know where this address was. But starting from the Pectra upgrade, because of a new feature that we added, the execution layer in the validity condition of the blocks, they need to know exactly where this balance is being held. And 3 execution clients forgot to add that address to their configuration. And 2 execution clients did add this address in the configuration. So when one of these new features came in, say, this block, then the 3 major clients consider it valid for one address, but then these 2 minor clients consider it invalid. And that's why what we call a consensus split happened.
Thank you. Naomi, do you have any questions?
Hello.
Yeah, hello, Glory. I can explain. So the question was, these attestations and block proposing, is it an automatical process, or you should do something for it, or it just goes automatically?
So yes, so the software does all of this for you. And so if you are from the point of view of the node operator, which is the person that actually runs this software, this node operator only needs to monitor the software, that is just to check that it's still functioning properly, but it doesn't need to do this to be constantly looking at this. It doesn't need to be any interaction. The software would just validate the block, would perform all of the duties. It would do all of this automatically.
Yeah, and the owner should update, right, as well.
Yeah, so whenever there is a hard fork, as what happened with Pectra, then anyone that is running the old software would be on an invalid branch once the hard fork is reached. So you need to change the software for a new version from time to time.
Okay, got you. So I'm wondering what could have caused an invalid block since this process is not manual. Let's say everything on my setup is okay and I'm just running my node and I'm running the correct validity of lines and all of that. So I'm just wondering what could have impacted on creating an invalid block.
Okay, so if you are in that situation where your node, it's a very unfortunate situation in which your node sees an invalid block as valid, and then you continue. So what will happen depends a lot in the client that you're running and the client that everyone else is running. So let's forget about Holesky for a second, and let's suppose that this happens on mainnet, which cannot happen exactly what the Holesky happened. But let's suppose that you're running a node. What happens is a problem in your computer, and it's only your computer and no one else's. And you get an invalid block, and your computer tells you this block is valid. So then what would immediately happen is that the next block will not be a child of the invalid block that you just synced. This is because everyone else would have seen this block as invalid. And then your computer would automatically take the next block and just move on. The chain would just continue with the next block. So you wouldn't see any difference. Now, if your computer had this problem, but it wasn't only your computer, it was like, say, 15% of the network had the same problem, then a bunch of people would have seen this block as invalid. But still, if it's 15% of the network, the next proposer will most likely be among the other set of validators that saw it as invalid, will propose a block, and every attester will attest for that block that is contending to your invalid one. So in all of this scenario, the same thing will happen. Like the next block comes in, probably I should put this on a slide, but the next block comes in and it reorgs out the block that you just saw as valid while it was actually invalid. So this means that in most of these situations, you don't need to do anything and the problem will solve itself in 12 seconds. Now, there is a problem if more than 50% of the chain has this bug. If more than half of the chain has the bug and the block is invalid and continues, now the whole chain will continue on an invalid branch, which is what happened in Cholesky. And this is why client diversity is actually very important. And also client diversity was kind of weakened by this problem because 3 different major clients had the same problem. But if only one of the 5 different clients has a problem, in principle, if the validator set is well distributed, only 20% of the network will see an invalid block as valid, and the remaining set of the chain will just reorg it out quickly, and you don't need to do anything. Now, if we ever face a situation like what Cholesky happened on mainnet, that would be a nightmare scenario that no one really wants to be put on, because recovering mainnet from something that what happened in Cholesky is today we do not know how to do that.
And if I update my node, will I go back to the right fork or not?
Oh, that's a very good question, but that's actually a technical implementation. So what happens is, let's suppose that we are in a situation exactly like Cholesky, where an invalid block was justified or finalized, it doesn't matter, and you were in that invalid branch and you started attesting on that invalid branch, and then you say, no, I want to go back to the valid one, and you update your software, and now your new software tells you this branch is invalid, and it doesn't sync it anymore. You're going to be following the chain on the valid branch, but your validator client will refuse to sign any attestation, because any attestation that you sign on that valid branch will slash you. So the validator client would refuse to ever sign any attestation. If you do sign an attestation, you will be slashed and expelled, and you lost money. And if you don't sign your attestation, anyways, you're going to continue losing money forever. So the only outcome for an honest validator in this situation is to exit.
And then I need to exit, I need to update and join the chain again, right?
No, so to exit, you don't even need to have your own validator. To exit, you can sign a message from any node. You can use a service provider. You don't even need to use your own validator.
Okay. And there is some period for slashing, right? How long is it? When you are slashed?
No, there is no period at all. You can be slashed by an offense that you did years ago. So any offense that you have, I mean, realistically, these offenses either are saved by validators or they're not. If no validator has your offense, they're not going to see it again. So then you might get out. But what happens in real life is that all of these offenses are recorded in the slasher, and eventually on each block that comes, they slash a new validator until all of them are going to be slashed.
Okay, sounds catastrophic.
So perhaps you might have been referring to a different timeline, which is when validators are slashed, the penalty is actually very small, except when many validators are slashed at the same time. The reason being that you don't want to penalize an operator that just made a silly mistake. If you just by mistake spinned up 2 different validators and got slashed, okay, tough bid, that's it. You would lose now, I don't know, 0.003 ETH or something like this. But the problem is that the slashing mechanism is there to protect the network from heavily stake operator that wants to double spend, for example. We want to finalize two contending branches. To do this, this operator will need to commit malicious acts with many validators at the same time. And then they will all be slashed together at the same time. So the way we deal with this is we collect all the validators that were slashed in the last 27 days. And after 27 days have passed, we looked at all the validators that were slashed. And if there are too many of them, we remove more money. We punish them much more heavily than if there are just a few of them. So we punish the validators 27 days after they are slashed. We punish them again according to how many validators were slashed during that period. So what's going to happen today in Cholesky is that 27 days from now, validators are going to lose a lot of money.
And the slashing, the penalties are different, right? It depends on the reason. Yes.
So the penalty goes from 0. So you get slashed at minimal penalty now, which is after the Pectra upgrade is very small, it's 0.003 or something like this, up to the full amount of your capital, the full amount of your, well, 32 ETH, or even more if you're one of the consolidated validators. So you may lose all of your capital if 33% of the chain is slashed.
Okay, thank you. Esli, you had a question as well?
Hey, yes, you said the two chains in the Cholesky would finalize eventually. I couldn't understand how two of them could finalize.
Okay, so let me give you 2 comments about this. So it seems to be in contradiction with what I said, that 2 contending branches cannot finalize unless 1/3 of the validators are slashed. But there's no contradiction here, because actually what will happen is that if the 2 chains continue and the validators just continue attesting without updating their clients, let me give you 2 different scenarios. Instead of going on the usual network partition, let me go on the other part. The other scenario, which is what will happen now. So what will happen now is that we actually are going to be 1/3 slashable, and that's it. But in the situation where no one updates their node, what will happen is not that they will be slashed, validators will not be slashed. What will happen is that validators on branch, let me call them branches A and B. Validators that are following branch A will see the validators in branch B losing money constantly, because from their point of view, whenever a block comes, the validator in branch B doesn't attest to this. When their time to propose a block comes, the validators in branch B don't propose a block. So they will start seeing that they are not performing the duties and punishing them slowly and slowly and slowly. Actually, when there's enough percentage of the validators that are doing this, then they punish them harsher and harsher and harsher so that we eject them. When a validator reaches 28 ETH of balance, it's expelled out of the network. And once the validator is expelled out of the network, it's no longer staking, so it's no longer supposed to attest, and it's no longer supposed to propose a block. So when this situation happens, we have a much smaller set. Every validator in branch A, before it was, say, 60%, but now it's 100% of the network, because they consider all validators in branch B already expelled. And then now they have 100% of the network, and they can actually finalize that branch. From the point of view of branch B, the exact opposite happened. And every validator on branch B is just expelled completely. And from their point of view, they are the only validators that are alive, and they finalize their own branch. So in this situation, it's not that one honest validator is seeing both branches. Validators from branch B will not even connect to validators in branch A, will never even see a block from branch A. It's like having 2 completely separate blockchains that don't even talk to each other.
Yeah, I see, but so branch A gets finalized, I guess, because they have the majority. I guess this is...
So if we don't update software or anything, both branches will have eventually 100% of their validators, because each branch will just expel the others. And from their point of view, they will have like all of their validators are still alive. So suppose branch A has 66%. the invalidators from branch A will expel the 33% of branch B, and now suddenly that 66 becomes 100%. And validators in branch B will expel the 66% of branch A, and then suddenly the 33% that they were will become 100%.
Okay, they got separated completely.
Yeah, they will be just like spinning two different Ethereum networks today, exact same clients, exact same everything, but different Genesis blocks.
Yeah, okay. Also, I was trying to follow this Holesky and I saw things like remote slashing database. These things happened. And but
So,
I also see they are still not finalized. So what is going on? Like I just want to.
okay, so now the situation is this, is branch A has an invalid block and was heavily voted. Branch B has a valid block, but doesn't have much weight. And we want to finalize branch B because that's the valid chain. We do not want to continue on branch A because it's invalid. The problem is that to finalize branch B, we could do two things. And one is just wait, not do anything, and wait until all validators in branch B expel those from branch A. That's what's actually going to happen. But so we could do that and wait a few days, a few weeks. It'll take a very long time for validators to expel. But once it happens, we will finalize. We were afraid that CL clients will not be able to handle the load of being a long time without finalizing. It is very heavy on CL clients to be on a time where we're not finalizing regularly the chain. And that's for a different story. But the thing is that in order to accelerate the procedure to finalize that chain faster, what we decided to do is to make the validators in chain A, the invalid one, to actually attest to chain B. So that we try to justify chain B by getting 66% of the votes on that chain. But we need a lot of participation for that to happen. And moreover, we have built-in software that even if we want to make a bad attestation, our software would prevent it, because a validator will never sign something that will make it slash, even if it's the honest thing to do. So validators that already attested to the invalid one, if they wanted to help the valid chain, they will have to actively slash themselves by attesting on the valid chain. And that was why we requested node operators to delete their slashing DB, which is the mechanism that protects them from slashing themselves. So that they slash themselves, but they move the weight to the valid branch. Unfortunately, we didn't get enough participation. Holesky is decentralized. There are lots of nodes operators that we do not know. And those operators didn't update their software. So we didn't get to the 66 that we need to justify it on branch B. But we got many of them slashed. That means that in 27 days, their balance would be almost zero, and they're going to be gone from the chain, and we're going to be able to finalize.
So we're just waiting, right?
Yes, we're waiting, but then also praying, because it's not really clear. So Lighthouse already has a bunch of problems with the state growth. I think every CL client is actually struggling. Essentially, client devs are managing to patch their client quickly and keep their validators, but normal users don't have access to these branches and are having trouble to keep their validators on. Now it's stable. So now at least it's holding up. We'll see if we can actually manage to save it.
That's a tough situation, and hopefully it's on testnet.
Yes. So luckily it's a testnet, and hopefully it will never happen again.
Yes, I hope so. Any other questions?
But it's also provided a good experiment, I guess, if anything that happens in the future, doesn't it?
Yes, it's definitely a good experiment.
Good and dangerous. Right. Any other questions? Please take your chance. Potuz is here. Ask your questions. We're running out of time, but yeah, the conversation is really great. If no questions anymore, I think we can stop here. Thank you very much, Potuz. Thank you for being here, for answering all our questions, for giving this talk. That was really, really helpful for us. Thank you very much. And
All right. Thank you
all
for the invitation.
joining us. Yeah, thank you.
See you
Bye,
guys.
everyone. Yeah,
Bye.
bye.